Awesome.
Great.
So hi, everyone. It's a genuine privilege to be speaking to so many of you. As Gabby mentioned, I'm a master's student at the University of Malta, doing some research here. And I'm actually doing half my master's here and half my master's at Trinity College with John Gould's group, and also collaborating with Steve Campbell at UCD. And what I work in is really taking a thermodynamic perspective to quantum information problems. So I know that's a mouthful, and we'll kind of really go through it quite quickly soon. And I also did a startup in my undergrad called Learned, which I'm now exiting and might die, but it's not my problem anymore. But yeah, so those are kind of the two things I've done. So let's talk about why thermodynamics is important for quantum computing, and why information is hot in a more general sense, okay? So in the late 19th century, Maxwell really got in tune to this idea that information is quite important to thermodynamics. So there's this very famous thought experiment called Maxwell's demon, where if you take a cylinder that's sort of split into bits, and bit not in the information sense, two parts, right? And there's these particles moving through the cylinder, and there's this demon that can kind of close and open a door in between, and these particles can move through. Just by knowing the speed of these particles moving, this demon can heat up this cylinder just by opening and closing this door. And then there's this guy, Leo Szilard, kind of built on this and made it a lot more concrete. So this is what I'd like to talk to you about. So this guy, Leo Szilard, he says, we can literally build an engine out of this. So if you have this cylinder and you have one atom moving through the cylinder, say, and you can then choose where to put this like end of a piston, whether it's at the very end of this cylinder or in the middle. If you are able to correctly guess where the particle is and you close it at the right time, you've increased the pressure, and that does work. So it's like you get work for free. But in truth, you don't get work for free. And let's kind of understand why. So a bit is, of course, two information states in some sense. There's a 1 and a 0. And we can imagine that the cylinder is like a bit, okay? So initially, the particle could have been at the front part or at the back part, but then when you choose where to put the piston head, you've kind of removed a bit of information. And very famously at the bottom of the slide, there is Boltzmann's equation for entropy, right? And entropy talks to us about these microstates, omega. So a bit has two of these things, and we've just removed two, right? So a bit of information, removing it corresponds to a change of entropy. And if we look at the first equation, which is just the first law of thermodynamics, that means that when you change the entropy, you've changed the heat exchange. And this whole reasoning is something called Landau erasure, okay? So when you delete a bit of information on your laptop, you should have heat exchange, which is a bit larger than this. So information is intrinsically hot. Really, it's a hot topic, and that's why we all work on it. And also, what I work on is kind of taking a quantum view of this, okay? So quantum mechanics is an even richer information structure, as all of you know. We have entropy, we have entanglement, we have discord, we have all these different funky types of correlations. And all of these things are resources within quantum algorithms, okay? So all of these quantities change during a quantum algorithm, and how these quantities change is going to affect the thermodynamics of the system. So you can imagine a quantum daemon that kind of stacks gates on different registers and maybe heats up the system, right? Or different parts of the system. And I'm thinking about these things. So let's zone in a bit more closely on my research. So very recently, I worked on this complexity class called DQC1, where we have one clean qubit and a fully mixed register. And this complexity class is known to solve trace estimation of unitary matrices. And here we've recently developed a relationship, which isn't even on the archive yet. So this is like a scoop, if you will, that the free energy of this first qubit is directly related to the size of the trace being estimated. So this is a really interesting result, I think, because it says that the computational work you're doing is directly related to the physical thermodynamic work you're doing. And I care a lot about these types of results. So this is what my research is like. But now let's see maybe, yeah, what my research is actually like, right? Like, what does it look like? So bottom left is really what most of the time looks like feet on the table, just thinking and being lazy. Bottom right is what it actually looks like, just Mathematica, plotting things, trying to solve equations, doing this type of stuff. Left is like when you get lucky and you go to the Swiss Alps to work on quantum algorithms with IBM. And right is, physicists are supposed to like whiteboards. So writing on whiteboards. But yeah, essentially, I think research is definitely about collaboration and talking to others and thinking out loud. And it involves many different things. So this is what I'm really trying to highlight here. Next up, yeah, my quantum journey. Okay, so I was very lucky that at 16, when I was in high school, I guess I formed one of these relationships like Caitlin was telling you. I reached out to a local quantum group. And I was like, hey, man, like, I'm really interested in these things. Can we meet up? And this guy, Professor Xuereb, I know we have the last surname, but we're not related, really took me under his wing and sort of helped me really find my feet in the area, despite my asking so many silly questions. He managed not to throw a book at me, which is very nice of him. So I'm deeply indebted to Andre. Elisa Baumer, who is someone who is Renato Renner's PhD student at ETH Zurich, I met twice. So I went over to ETH twice for summer schools during my undergrad. And these were really pivotal moments for me because like Malta is so small. The amount of people that do quantum here are maybe like, I don't know, 20 plus people, really, really small numbers. So to get to go to a place where there are many, many people all interested about this was deeply meaningful to me. And one of the people I met there was Elisa, and I was able to work on this project with her. And she really held my hand during the initial steps of this project. So I'm very thankful to her also. And third is Dr. Tony Apollara, who is let's say the other co-leader of our group here, who is this really brilliant solid state physicist who now works on quantum information and who I've had some really great mental sparring sessions with over a couple of months. So those are three people I'm deeply indebted to. And two big moments are these. So the top one is at this quantum information summer school at ETH, which was, like I said, the first time I really met a lot of people that do quantum and was super exciting for me. And the second is presenting at this Qubit hackathon, like I said, at the Swiss Alps, which was really cool. It was like my first research experience working on a problem. And that was a really great opportunity as well, working with all these people. And I really do invite you to pursue these opportunities. There's these opportunities by Qubit, by Xanadu, I think, do QHack. So there's all these different opportunities which you should all go for. I mean, you're doing Qubit by Qubit, which is already awesome. So definitely go for more. Tips, let's see, what did I say? Yeah, man, pursue what you enjoy with great intensity, but don't treat it like a competition. Academia really, you can really get into this weird mindset that, oh, I need to get the highest grades and all this. No, it's about doing what you do to create beauty and to share it with others. That's what being human is about, and doing research is a human endeavor, so enjoy it. The best opportunities are low probability with high rewards, so take risks. Email people, don't be afraid to email people, even if you think they won't reply. There's always like a non-zero probability. The question you're asking is always more important than the answer in research, right? So the way you frame a problem is super important. And don't be afraid to be multifaceted. So when I was doing my startup in undergrad, it was really tough managing everything. And I used to get a lot of flack from professors for doing a lot of things. But I think ultimately it's really made me a more well-rounded person, capable of more things and exploring different mental horizons. So I really recommend doing that. So thank you for listening. And yeah, do reach out if you ever want to chat about anything. So let's see if you guys have any questions.
We had one question. Thank you, first off, for that awesome talk. We do have one question from Joseph, who asks, how do you control heating on such a small atomic scale when you're talking about something like quantum thermodynamics? Like, what does it actually mean to control heat in that level?
Yeah, these are extremely good questions that like I think about. So, I mean, even talking about work in a quantum sense is really tough. So like, there's no observable we can relate to work even. And even in those regimes, we have non-equilibrium thermodynamics, which is weird. So oftentimes what you'll do is you'll take an equilibrium state at the beginning and at the end and kind of say what happens in the middle, right? So it's tough, but what we can kind of think about is say, if you look at this quantum process, right, what's it trying to achieve? What resource is it using to achieve this goal? And how is this related to thermodynamics? And making sure that this algorithm is not being wasteful. So let me phrase it in the context of unitary trace estimation, for example. So some of these unitaries need entanglement to have their trace estimated, others don't. Others are literally efficiently estimatable using classical algorithms. So in that case, make sure that you're optimizing your data set so that you're only using say the powers of quantum mechanics when you need them, because this will be more thermodynamically efficient, right? Because you're not being wasteful. But really, these ideas of optimization are very early in the sense that we're really just getting at the foundations of this stuff. Like, not many people have really looked at these ideas, but it's great that you're thinking about this stuff, because it's what I'm thinking about. And we really need to make sure that quantum computers are scalable, right? Like, what if it's the case that these things heat up as we use them because they're so, like, they need to be in such perfect conditions? We need to worry about this, and maybe, you know, even error correction, right? Does error correction cool the systems? Ideas like these are things I like to think about.